Systems are always adapting to seek opportunity in the face of constraints, producing growth success, right? But also preparing to be surprised at the boundaries of how their system works and is changing, the ability to handle challenges that arise. Other units are adapting too, right? Seeking advantage, handling challenge. So what does this produce, given the constraints we've identified so far? One is that they are layered networks of different adaptive units. Layered, right? And a network with interdependencies. Now, we refer to these as tangled layered networks because literally the interdependencies get all tangled up. They are not neat and easy to lay out, and we'll illustrate that with real cases, stuff taken from different sectors. Tangled layered networks, or TLNs, arise naturally given the basics that we've laid out so far. Resources are finite. That means conflict will be ubiquitous. Change is continuous. So the models on which we base our developments and improvements to handle variation in the world, right, will become stale, and surprises will happen at the boundaries. Now, the second aspect that turns out to be fundamental is trade-offs. There are multiple trade-offs that have to be balanced. It's not a single trade-off. It's actually a multidimensional trade-off space, an n-dimensional trade-off space. As we pursue and understand more about trade-offs and how to plot trade-offs and how to maneuver or navigate trade-offs, how to change your position in this multidimensional trade space, we'll talk about some of those trade-off dimensions. We think there might be 5. But the exact number isn't important, but the issue is how do you navigate and adjust in the trade space as things change? Now, we'll discuss the usual way people think about how to be optimal in the face of trade-offs, but it turns out to be a little different because the trade-offs are always applicable, limiting what you can do, and it creates this puzzle for us. How do we take subsystems or components that are in one place of the trade-off space? Now, they could be in another place, but whichever place they're at, there are limits on their performance. Now, how do we put them together into a larger system whose emergent properties and performance capabilities are more than those of the components? So that components, we'll talk about this in the context of Eric Holnagel's efficiency thoroughness trade-off. So they might be faster, or others might be more thorough. But which should you be when? And even if you should emphasize speed, all right, you still need to be thorough in some ways. You can't just abandon or reduce thoroughness. You have to readjust how you achieve some degree of thoroughness relative to speed pressure under some circumstances. Well, what does that do? Well, we'll look at that in different contexts of natural disasters. We'll look at that in terms of overloaded emergency rooms in a hospital. We can express these different fundamental ideas in these concrete settings where we observe the patterns of adaptation play out. And we'll see how we can adjust on other trade-off dimensions when we have to make a trade-off on speed thoroughness due to pressure or new challenges arising at the boundaries. The third fundamental is a theorem called robust yet fragile. Now, robust yet fragile emerged as a theorem about 23 years ago, right? And it highlights a fundamental. And similarly, about 23 years ago, research on safety in complex systems, how we succeed and create safety and yet sometimes have failures of these high-risk systems in aviation, space, medicine, energy, transportation, etc. Right? We recognize the empirical pattern, right, that systems can be brittle. Again, because resources are finite, change is continuous, right? Brittleness is omnipresent risk, right? Fundamentally, systems have to be designed and architected in order to offset the risk of brittleness, regardless of where we're operating in the biological space, whether we're dealing with organizations, industrial sectors, whether we're dealing with societies, whether we're dealing with human and systems that include sophisticated forms of technology, automation, autonomy, intelligent systems, artificial intelligence in one or another form. No matter how we look at it, there is an envelope within which we are competent. There are boundaries to that envelope, and there are challenges that occur on the edges of that envelope. We will illustrate that in general, and we will explore it in the particular settings, accidents, near misses, ways that systems function despite the risk of brittleness. Across biology, no matter where we look at it, from cells to human societies, right? Biology abhors competent but brittle systems. Biology develops ways to be extensible at the boundaries. That's what we laid out in handling challenge. That extensibility is fundamental, yet it is often overlooked in how we as people reflect on the systems in which we act, which we develop, which we are stakeholders in.